So Bryan is a vice president and group CTO at Autodesk. I was asking him when we met what exactly he worked on, and he sort of gave me this long string of different products and areas that he focuses on. So he's got some really interesting breadth of experience here at Autodesk. Let's give him a warm welcome. Thank you, Bryan.
All right, thank you. Is the mic working? Here in the back? Great. So, you know, I am a tool maker. Autodesk, we make software that helps people design things. I'm not a designer. So when talking to this audience, what I decided to share with you is just some thoughts and some things that I've been tracking about these trends that are happening in the design space. And my remote, it's not working. Let's try that. When most people think of design, they think of this cliche. It's the shape, it's the noun, it's the beautiful product. And when I talk to designers, that's usually not what we talk about. We talk about design not as a noun, but as a verb. If you think of design as a verb, we're talking about a way of solving problems. And the world's got a lot of problems that we're facing today, whether it's global climate change, the rising cost of energy, how we're going to feed and clothe up to 9 billion people on the planet, our aging infrastructure. We got some major design challenges. How are we going to have a sustainable economy with limited resources? Those are design challenges. And so I think it's really exciting. You hear people like Chris talk about how the way things are made, the way things are designed, is being democratized. And so as a tool maker, that makes us very excited here. Our mission is to help everyone imagine, design, and create a better world. And so what do we mean by that? Well, when we think of the tools that can enable that, it's the tools that help people like you design the machines, or the machines that make the machines, or the buildings that we live in, or the systems that run the buildings that we live in. It's the cities that we live in. It's the infrastructure that empowers that city. And it's also the products that we build. A lot of design is in things like this, entertainment, for example. You may not think of it, but a lot of the tools that I have been involved with are used in things like filmmaking, so virtual worlds. And that's a great idea when it comes to design, because design as a process is an iterative process. And so what all of this new technology is allowing us to do is to create alternative realities, taking your ideas and turning them into a digital reality before you make the real one. Before you muck up the planet, you can have a beta. So what are these trends? Well, we're going to go through a number of them. The first one that I think is really changing the world is what we call reality computing or reality capture, which is the idea that reality is really complicated. If you think of this as the reality that you want to make a change to, or if you're an artist and you're working with the complexity of even just that one piece, or if you're trying to build a stadium. There's a lot of complexity in the world, and there's all these tools. Technology allows us to model that. But the dirty little secret is you start with a blank sheet of paper. And it's very hard to get from that complexity to there, and it's not very democratized. And that's where some new technologies have come in. Amory Lovins, who was trying to make the Empire State Building more sustainable, it took him 9 months to come up with a digital model before he could run his first energy simulation. But nowadays, these new devices, these sensors, this explosion of sensors, and you hear people talk about Internet of Things, and this relates to that. These sensors can make these 3D models almost instantly. So this is what's called a point cloud from a laser scanner. It takes a picture of its environment, not in 2D, but in 3D. But this isn't democratized as well. It's kind of like you go to a doctor's office and look at an X-ray. The doctor knows what they're looking at, but you probably can't interpret that fuzzy data. I know what I'm looking at here, but let me show you how software tools can democratize that. This is the exact same data set you were just looking at. It's just shown in a more modern way. And it's showing you how fast technology is advancing. This is a 3D photograph. You can move through this data, and this is what's scanned by a laser scanner, billions of points. So how are people using this? Well, the big change for designers as you design things is that now you can design in context. So I think that reality capture trend that we're talking about is about doing design in context. We've always done design on that one sheet of paper in our heads, and it's gone from here to documentation. And really what we can do is have the whole context of how our product or our idea gets designed. Another way that we're doing this isn't just by capturing the shape of things with things like laser scanners, but any kind of analog data, that Internet of Things. So we did this with our office building. We put a bazillion sensors on every electrical outlet. Every chair in the office had all of these sensors on them. We made a digital model of our office building. Every elevator, pump, every HVAC cooling system, all of that for an entire building, and all of those sensors. And it made really what's something that's alive. And I think that's another important trend about design today. It isn't just about the shape of the product. We're seeing mechatronics, electronics, software, and shape all come together. And so even buildings, which you wouldn't think of being like a Pebble watch, are now like a Pebble watch, where they're as sensor-rich as your cell phone. And so that brings context into design. And so we have to kind of change how we think about how we do that design. So here we can do simulations to make this building more sustainable. You might have driven your Prius here today. Transportation is only about 24% of greenhouse gas emissions come from that. About 25% comes from meat production, and 42% comes from buildings. So that's a big opportunity there if you're into that. So what is this? This is another form of reality capture. Anyone know what a BRDF scanner is? Never gotten a single person. Of course, it's the bidirectional reflectivity distribution function scanner, otherwise known as a material scanner that allows us to do this. So if you've seen any kind of special effects, you're looking at this kind of BRDF stuff. One of these is real, one of these is fake. And how many people think that's the real one? This one? Okay. I'm not telling you which one. But the important thing is our ability to take the world and make it digital, okay, extends right down into the physical properties of the materials. And so you see that happen in things like the entertainment industry, where we take Jeff Bridges and make him look 30 years younger by putting him in this little device here. This is a geometry and material scanner. It simulates how the photons of light go into your skin, bounce around with your blood vessels and fat cells, and then re-emit back out in different directions. That's me inside there. They haven't turned it on yet. When it's on, it's about 4 times brighter than the sun. And if you've watched Iron Man or the Avengers, those guys have to hold a pose without grimacing. I was crying. It was so bright it hurt. But this technology, one of the things that's happened recently is this democratization of reality capture. The phone that's in your pocket right now can capture reality. There's this process called photogrammetry, where you take a bunch of pictures of some complex object. Okay? It would be very hard to get that into a computer. But here's somebody's dining room table, took some pictures. You can see them there in the background. This was the source material. Threw that up to the cloud, let a supercomputer crunch on this for about an hour, and this is what you get back. A 3-dimensional model, all just from a number of photographs. Now to do that, it has to figure out the lens distortion, the offset of the CMOS sensor inside of the camera. I mean, the mathematics of this is incredible, but it's democratized because you don't need to own any of that, right? You can have the cloud do tons and tons of computation. And I think that's really exciting. Another thing that this kind of technology is being used for, if you think of the Leakey family, Louise Leakey in Kenya is taking all of these 20,000 fossils that are locked away in these vaults that no one ever gets to see, photographing them and putting them online. So the implications on education or even design. Think what happened in the music industry, where we could remix a song by taking other samples. And we're seeing this increasingly. Why don't you take Early Man and remix that into some piece of art? Or Sly Lee here, who's working with the National Park Service, studying the acidification of oceans and how that applies to things like coral reefs. Wouldn't it be neat to have a piece of designed artwork in your home that is a 3D printed coral? Okay? Or have your next product, the handles of it, of your bicycle, come from coral? Well, he's doing this for scientific reasons, but you can also get a beautiful result for design purposes, that idea of remixing, remashing different inputs. So by taking those photographs under the water, we can get 500,000 3-dimensional points from that, and then get these kinds of models. We've even been applying it to things like this, bringing back history. Anyone know what this is? Yeah. The Bamyan Buddhas in Afghanistan, the Taliban about 14 years ago blew these beautiful structures up. And all that remained were a bunch of Associated Press photos that I downloaded over the web, crowdsourced, and threw it up to the cloud, and we rebuilt them digitally from the historic photos. So now we can go 3D print the Bamyan Buddhas again, or you can recarve them into the mountainside. So I think this trend of reality capture has many different applications. Another one, again, sustainability. We just heard Chris talk about drones. One of the use cases for that is flying drones with cameras now over buildings. And you have Marriott here making 3-dimensional models of their buildings, running them through a cloud-based energy analysis system and telling them where they should spend their budget to make their hotels more efficient. That's pretty exciting. All right, so we've captured reality, but what's the next step? Whether we're getting sensor analog data or shape data, the result is a heck of a lot of data. And data is useless, okay? We're going to talk about data, I think, later today. Data by itself is useless, and there's a lot of data out there. I mean, this is just one wing of one hospital here in San Francisco, the Mount Zion Cancer Research Center. And look at just the complexity of that. And then you think of a whole city. But then there's all of the systems underneath the ground, the infrastructure that connects all of this stuff together, all sorts of product data about how these systems work. Okay? And what we're talking about is being able to design in context again. So not just capturing reality, but now having all the data about that reality and centralizing data in the cloud. We've seen what Google has done with a lot of the textual internet. Now we think this ability to search on centralized data is going to have a lot of design implications on you. You know, Chris talked about how you can learn from the web on how to be your own manufacturer. There's many other things that I think centralizing all this other data are going to do in the future. So one idea of this data is if you're doing an infrastructure design project here, what kind of bridge should we use? Here is a system going through various iterations. It's looking at where the wetlands are, where people's houses are. How do we disrupt the fewest number of people, the least damage to the environment at the lowest cost with a signature beautiful bridge? And all of that stuff can be visualized in context in real time through simulation. Pretty impressive. And what you're seeing here, if you've seen what IBM's Watson, if you watch that Jeopardy program, what it does is kind of an artificial intelligence system. We're actually teaching machines effectively how to think in certain restricted ways. And you're looking at here as a kind of a map of a computer that's learning everything about design. We have a lot of our customers' design data that they've put into the system, and we had this AI system churn on it and try and learn design principles from prior people's work. And we find that's fascinating. So we started with reality data, right? That turned into centralized cloud data. We want to turn data into information, answers, and insights. The next step is that we want to compute on that. I think this is something that the press really hasn't been picking up on. They've been talking about cloud computing a lot. But we have something we call infinite computing, which is kind of cloud computing turned a little bit on its head. Instead of seeing how many people can fit on one Salesforce server, what if we invert that? How many servers can I devote to you? So put another way, if you watch the movie Avatar, each frame of animation in that movie took about 72 hours to render. Okay? 72 hours for a 2-hour movie, 24 frames a second, but it's stereo, so it's 48 frames a second. That's a lot of computation. And each one of those frames is about 250,000 seconds on the fastest Intel processor. So you could buy one of those computers, amortize its value over time. The price of electricity is about $50 a frame. Or you can go to the cloud, and you can rent 250,000 computers for 1 second, do the exact same number of math, the amount of mathematics, and it costs the same amount of money. This is the first time in history that improved performance. The performance of a Lamborghini costs the same as the performance of a Camry, right? There's no premium for getting something done faster. And so how is that going to change how you design? Well, this is the old way that people designed. You've got an idea in your head, document it in a computer, run a simulation. Simulation says that chair is going to fail, it's not going to survive in an accident, or it's going to cost too much to produce, right? You see too much red in it. Well, another way that you could change how you fix this design, instead of just coming up with another iteration and playing Battleship, E7 miss, right, is tell the computer to go get 10,000 computers and run 10,000 different simulations of slightly different designs, and have the computer tell you which is the most optimal. So this algorithmic approach, I think, is going to be very interesting to the future design. Not only are we going to take all this cloud information and get contextual information, but we can get insight from deep computing itself. Now this, David Benjamin, this is a researcher that's working at Autodesk who is taking buildings and running computational evolution. So you take a building and think of everything about this building as being DNA. So the amount of insulation in the walls is a gene, how big the windows are is a gene, all of that, the orientation relative to the sun is a gene, all these design choices. And how does nature come up with a solution to a design problem? It evolves. And so if you get 100,000 computers and they all do 12-hour simulations on these buildings and find the buildings that are most successful, you take the successful buildings and let them have sex. And they have a bunch of children. And those children go through a fitness function. They go through a simulation. And the most fit buildings that are the least expensive, most safe in an earthquake, most environmentally most friendly to live in, have best lighting conditions, all of that stuff are allowed to procreate and survive. Survival of the fittest. And you throw in mutations from a product catalog. This researcher did 25,000 12-hour simulations. You can't do that on one workstation, but with the cloud, it's pretty interesting what you can do. So let's apply that to a product like you might make, a chair. So here is the design requirement. I need to have a chair, it's this big, these dimensions, and it has to hold this much weight without failing. If you want to lightweight that chair, reduce its cost, an expert designer might lightweight it this way. But what if we use computational evolution? We go up to the cloud, use a couple thousand things, and let it evolve a chair. What does an evolved chair look like? Okay, it looks like that. That is a non-obvious solution, but it actually performs better. It's only 2.9 kilograms, significantly lighter than what a human-designed chair was. It performs better, more environmental. And the neat thing about 3D printers, and we'll get to that in a second. I'll talk about 3D printers in a little bit. So we've been working with Airbus. Airbus is applying this computational evolution of design to airplanes, lightweighting the airplanes, and you get something that looks like the cross-section of the bone of a bird. We call this biomimetic design. It's mimicking how biology works, and we think that is a more sustainable way to think in the future. Janine Benyus has done a lot of work in that area. All right, captured reality gives us context. Turn data into information by centralizing it in the cloud and applying infinite computing to it. The next step, the next big trend, I think, in design is around simulation. So visualization, simulation, and analysis. So there's all sorts of different types of simulation that you can do. Lighting simulation, thermal, okay, rendering, and so on. You can even simulate human beings. If you've seen some of the more sophisticated video game technology out there, we use those kinds of engines. We have one that we can apply to things like an emergency evacuation. Or simulation like this. This is a great story. If you want to, part of design is, of course, trying to bring the public along with you. If you've been up in Seattle, you've probably driven over this road here. It's not safe, and everyone knew it wasn't safe. And so they put it out for ballot to get it replaced, put it in a tunnel. And the public didn't want to pay for it. And so Parsons Brinkerhoff went and did a simulation and a visualization of that. The city government had it blocked. They thought it was too damning. And the local news station, under the Freedom of Information Act, got this video released. And guess what? The year after that, it was funded. It's amazing the power of simulation. Other simulations that you can do, whoops, there we go. This is some neat stuff that came out of the video game industry. And I think this is a lot of where innovation can happen, is take ideas that happen in one industry and apply them somewhere else, or combine different ideas. And that's what this was. This is real-time computational fluid dynamics being applied to different types of problems. And this really came out of the movie industry. When you watch Avatar and you see those waterfalls, that's computational fluid dynamics doing all that simulation. But what if you could get that simulation, because of the cloud, to happen while you're designing? Instead of simulating whether this product is going to be safe or effective at the end of your design cycle, how about doing it while you're designing it and getting sustainability feedback at the same time? This is another great example of that. Here you are in an operating theater, and it's showing you, it's making the designer able to see the airflow that's usually invisible. And they use HEPA filters that take out all the viruses and bacteria in the ceiling there, but as it mixes, it picks up everything on the people around it. But if you can see while you design, you can move the air vents in the room and get feedback like this. And I'd much rather be in this operating theater than the first one. We've even been applying some of these simulation technologies at the nanoscale. So this is simulating actual molecules and how they come together. And I think this is a new area. If you think of the internet as being one huge trend that's changed design and all that, I think biological processes are really going to change things in the future. In fact, we're partnering with a number of small startups. BioBricks is one of them, who has been treating biology as a programming language and a compiler and a computer all in one. So think of a cell, and you have if-then statements that you encode in DNA, and yeast runs your program for you, okay, to construct something. It's pretty cool stuff. There's even high school students doing this in the iGEM competition. So the last part of this trend, after we captured reality, turned it into data that we centralized to make information from it so that we could do infinite computing on it with our simulation technology, is we need to bring it home back into the analog world where we live. So how do we do that? One way to go from the digital world back to analog is through rendering. If you've watched any of these movies or things, by the way, all of these are fake. Almost every car commercial you watch is fake because those products have to have their marketing materials done long before the factory makes the first item. Okay? So when you see those ads, now you know. And that's why they generally don't like putting humans in them, and they tint the windows out because it's a pain dealing with fake humans. She's fake too, by the way. She was done 10 years ago. The technology today is much better. All fake. The last 19 years, the Academy Award winners for special effects were all using our virtual tools, and that's how you make a virtual world. But rendering is one way that you can take the digital back into analog, and that's a great way to democratize, because every product that you make really has a story to tell. And so how do you tell that story? How do you really connect with the customer? Design is almost as much emotion as it is solution. But there's these other technologies. Certainly in manufacturing, you know all the old school things, but there's the two new ones, which is additive manufacturing, which you guys know is 3D printing, or this new bio-nano stuff, which is pretty cool. So again, 3D printing, you got a CAD model, you put it on your 3D printer, and it comes out already assembled. And the neat thing about 3D printers is that complexity is free. Think about that for a second. Any other type of manufacturing, whether you're cooking dinner tonight, manufacturing a meal, or you got a lathe and you're manufacturing something from wood, the more complex the shape is that you're trying to make, the more expensive it is to make, the harder it is to make. On a 3D printer, the opposite is true. The printer does not care about the complexity. It only cares about the quantity of material. So the more complex shape you make, like that chair or that Airbus that we saw earlier that had that super complex organic shape, it's actually easier to make on a 3D printer than something that's just a blob of plastic or metal. We've been open sourcing this out here. You'll be able to see Autodesk. We've been just dabbling in hardware with this platform, trying to make an open source platform for 3D printing and getting that into schools and education and so on. But what's interesting is the number of materials that can be made. These multi-material printers that can do circuitry and material together are very interesting in the future. Over 100 different materials that can be printed today. So people are 3D printing drugs, 3D printing food, 3D printing a car, 3D printing the earth. If you go to Disney, they take their design for where the theme parks and the island and the canal and all that stuff are going to go, and they put it on there. You can see the differential GPS on the truck, and the guy drives it back and forth, 3D print the earth. Professor Kushnevis has been 3D printing buildings. And if complexity is free, you'd think they'd do something a little more complicated than an ordinary office building, something a little more beautiful. And certainly the grad student here who's standing in front of, behold, the vertical wall, the most boring shape that you could make on a printer that doesn't care about complexity. But that's pretty exciting, the implications of that. But people 3D printing clothes, 3D printing art. This is an example of bringing these two things together. And this is the next trend that I think is important, which is personalization. It took pictures of this VC, took inspiration from Greek sculpture and some movies, and this artist remixed them, all of these things together, to take that VC as a gift, put him in the Greek pose, inspired by these movies, and then make a fake bronze out of it. So, personalized one-off projects. And the 3D printer doesn't care if it prints one Nike shoe or a million. And so in the future, we're going to have 3D printed things like this that are very custom and personalized. And the thing that empowers that is the ability that we can do the reality capture of your arm, and then we can do the computation, kind of rip, mix, and burn of atoms, as Chris Anderson likes to say, rather than of atoms rather than bits. And Nike's doing this with their Flyknit shoe. This is effectively a 3D woven shoe. Its shape is defined in software, not by a mold, not by a hardware jig. Another example of that, again, is this Within Labs, which can lightweight parts and make them more sustainable. Over here at Pier 9, right here in San Francisco, we've got a lab at our other office, which has one of these 3D printing stem cells, a partnership with Organovo. And so we can actually 3D print organs. They've been working on ears over there. The problem is when the stem cells grow and specialize, even though they started out as an ear shape, they end up as something else. So we're using that simulation to say, well, if I print this, how do I get it to arrive at an ear? How do I play the physics backwards? So that's pretty interesting. Yeah, there's some of the ear. And we've also, Autodesk, just down at Pier 9, it's only the third time in the world that someone's done this, but we have a synthetically printed virus. We took a virus, reality captured it, turned it into a text file on a computer. It's a very common virus that's found in your gut right now. put the word Autodesk in it, and then put it on a synthesizer, synthesize that DNA, which made it as it came back from a lab in a vial, and then we had to boot it up, get that thing to fold back into a 3D virus shape, and it went in and killed bacteria as that virus naturally does in your gut. So pretty interesting if you can think of our ability to now design biology to solve a lot of the problems. So if we want to make our fuels, if we want to make our buildings, imagine a bridge that you change the DNA of a tree and it grows a bridge, and if it gets damaged when somebody drives a car into the guardrail, it grows back, it heals itself. And I think that's a future that is not going to be impossible. We're already seeing it at small scales. And even using this is DNA being used structurally, not as a living thing. Think of DNA like a 2x4 or a pipe, and you can put charge on it by designing the DNA in the right way and make nano-sized machines, little robots, nano-robots. And so I think the future design of that is amazing. This is real. So there's a CAD file of a design, and this is actual scanning electron microscope of real DNA that's self-assembled into that shape that it was told to self-assemble into. So Sean Douglas and the Wyss Institute at Harvard are all working together with us. We've been simulating this. This is the cure for cancer here. It is self-assembled DNA that's a box, and you put in very toxic chemotherapy or a hormone that's in there that can tell cancer cells to kill themselves. This box, you inject it in your body, it bounces around, it doesn't do anything, but that little red zone is a chemical marker that will bind onto only cancer cells, open and deliver the payload. So pretty interesting stuff there as well. So that kind of takes us full circle. We started with reality. We can bring context to everything that we design. We can compute on that reality, right? And simulate all of our mistakes before we make them real, iterate on them in a design process, and then bring them back into reality. So capture, compute, and create. And that fits into Imagine, Design, Create, which is really our mission. So, I hope you guys all get inspired to go out there and really build the kick-ass next piece of architecture, or go out and help somebody live a better life with something like this prosthetic, or create the next very cool video game, save the planet with some kind of cheap energy, or make the world's best Halloween costume that emits thunderbolts of lightning. So with that, thank you.